Soulful Scents has found that the marginal cost of producing X ounces of a new fragrance is given by C prime of X equal to 0.0005x squared minus 0.1x plus 30 for X less than or equal to 125, where C prime of X is in dollars. Use 5 subintervals over the interval 0 to 100 and the left endpoint of each subinterval to approximate the total cost of producing 100 ounces of the fragrance. Let's begin by graphing this function C prime of X in our graphing calculator to get an idea of what the function looks like. So in our graphing calculator, we're going to select y equals and then enter our function under y1. Next, we need to set our windows. So selecting window, we're interested in approximating the area under the curve over the interval 0 to 100. So I've selected x min to be 0 and x max to be 100. Also, after taking a look at the graph, I found that by setting our y max to be 50, we're able to get a good picture of the graph. I selected the y min to be 0 because it really doesn't make any sense to talk about x being negative, since x refers to the ounces of a new fragrance. So x is going to be positive. So I set the min to be 0, the y min. Next, we're going to hit graph, and there's a picture of our function. Notice if you're interested in what our y-intercept is here, if we plug 0 in for x into our function, hitting value and selecting 0, our y-intercept is at 30. We could also see that by just evaluating the function at x equal to 0. So let's just make a rough sketch of the graph that we graphed in our graphing calculator here, C prime of X. So our variable x along the x-axis represents the ounces of a new fragrance, and then along our y-axis is our marginal cost function, C prime of X. And just kind of a rough sketch, the graph looks kind of something like that. And our intercept, our y-intercept, or C prime x-intercept is at 30 there. Alright, so we want to approximate the area under this curve from 0 to 100. And we're going to do that by creating rectangles. And we're told to use 5 subintervals. So we're going to have 5 rectangles here. Let's begin by finding our delta x to determine what the width of each rectangle is. So our delta x, to calculate that, we do b minus a divided by n, where b and a represent our endpoints of our intervals. So 0 is our a and 100 is our b. So subtracting those. So 100 minus 0 divided by n, and n is the number of subintervals that we're told to use. So in this case we're told to use 5. So we're dividing by 5. So 100 divided by 5 is going to give us 20. So the width of each of our rectangles is 20. So next what I'm going to do is I'm going to draw each of those rectangles to get a visualization of what we're doing here. So each triangle has a width of 20, and there's a total of 5 of them. There's 1, 2, 3, 4, and then our 5th one there. And then we're using the left endpoint for the subinterval. So using the left side of each rectangle. So here is our first rectangle using the left side. There's the second one using the left side, so that means 20, our function value at 20 is the height of the second triangle. Third triangle, fourth triangle, and then the 5th triangle. So now notice by calculating the area of these 5 rectangles, it gives us approximation of the area under the curve between 0 and 100 on that interval. Notice in this case, because each of our rectangles is a little bit bigger than the area under the curve, the approximation is going to be slightly higher than the actual exact area under the curve. But it gives us a good approximation. And remember, the reason why we're doing this is because the area under the curve is not a nice geometric shape that we can calculate the area of. It's a curve. Therefore, we're creating these rectangles to get an approximation. Now when calculating a Riemann summation, kind of our general equation is using this summation notation from I equal 1 to n for our function at each of our x sub i's times delta x. So this function value times delta x is calculating the area of each rectangle, and then we're summing each of those up. Since we have 5 rectangles in this case, we should have 5 terms in our Riemann summation. Let's modify this general equation to fit our scenario here. In this case, our n is 5. So let's change our n to be 5. And then instead of using f for our function, we're using c prime of x. Alright, so there's our Riemann summation, and if we write out each term, it's going to look like the following. We're going to have c prime x sub 1 times delta x plus c prime x sub 2 times delta x plus c prime x sub 3 times delta x plus c prime of x sub 4 times delta x plus c prime x sub 5 times delta x. So there are our 5 terms. Alright, we know that delta x is 20, and we know each of our x sub i's. For example, x sub 1 in this case is 0 since we're using the left side of the rectangle. This is our x sub 1. And then our x sub 2 is 20 because we're using the left side of the rectangle to approximate the height. And then our x sub 3 is 40, our x sub 4 is 60, and then our x sub 5 is 80 because we're using c prime of 80 to give us the height of that last rectangle. So here we have c prime of 0 times delta x, which is 20, plus c prime of 20 times our delta x, which is 20, plus c prime of 40 times 20, our delta x, plus c prime, and then our x sub 4 is 60 times our delta x, which is 20, and then our last one there, c prime of 80 times 20. So I just want to point out what each of these terms represents. So this first one here, c prime of 0 times 20, what that first term gives us is the area of this first rectangle. The width of that rectangle is 20, and then the height of that rectangle is given by c prime of 0. C prime of 0 is 30, because we already found the intercept there along the y-axis. And then our next term, c prime of 20 times 20, that term gives us the area of the second rectangle. Again, the width is 20. Each of the rectangles has a width of 20. And then the height of this rectangle is given by whatever that function value is there. Whatever c prime of 20 is, and we'll have to calculate that. That gives us the height of that second rectangle. Alright, so now let's finish calculating this. C prime of 0 we said is 30 times 20 plus, and then c prime of 20. If we plug 20 into this function here, we get 28.2. And then that's being multiplied by 20 plus c prime of 40. If we plug 40 into c prime of x, we get 26.8. And then that's being multiplied by 20 plus, and then c prime of 60, plugging 60 into this function, we get 25.8 times 20. And then the last term there, c prime of 80, plugging 80 into the function, we get 25.2, and that's being multiplied by 20. Alright, and then calculating all this and simplifying, we get a total of 2,720. And this is dollars. So what this tells us, it gives us approximation for the total cost of producing 100 ounces of this fragrance. Because remember what we did here, we graphed the derivative, which is the marginal cost, c prime of x. By getting an approximation of the area under that curve over the interval 0 to 100, it gave us an approximation for the total cost. Now, in general, anytime we're calculating this Riemann summation to approximate the area under a curve, we need to realize that the more rectangles that we use, the more subintervals we use, the more accurate the approximation is going to be, because we're going to get a better fit under that curve. And so as the number of rectangles increases, the width of each rectangle, which we call delta x, is going to decrease. And if we kind of think about the idea of, well, what happens as our subintervals increase and get bigger and bigger and bigger, think about approaching infinity, our delta x's, the width of our rectangles, are just going to get smaller and smaller and smaller, and eventually they're going to approach 0. And so our Riemann sum is going to get closer and closer to the exact area under that curve. And what we're going to learn next week is that exact area under a curve over an interval is defined by what is called a definite integral. And we've studied integrals this week, and we're going to continue that idea next week, and we're going to learn how we get the exact area by using a definite integral.